Okay, all right. So it has started recording. So welcome back. So where are we now? I think we must have finished certainly time-wise half the course, and maybe content-wise, I don't know, half or less than half. We will see. And so we have finished fully now the first two chapters of Lang, and today we will start chapter 3. So chapter 1 was more global in nature, and chapter 2 was local in nature. You must have seen that in chapter 2, some analysis played a role, completeness played a role. And we will come back to more global stuff in chapter 3. And that's what we will do today. We'll start doing today. Okay, so let me share the screen. And yeah, so today is lecture 15 maybe. Yeah. Okay, so one of you could confirm that you can see the slides. Yeah, please confirm.
Yes, yes, I tell you.
You can. Okay, so I'm starting with a typo. I forgot to change this. So this was last time. We are starting with something else today. Okay, so that I will change. So last time we discussed the periodic fields, and we looked at in the class before the last class we did unramified extensions in some detail, and last time we looked at totally ramified extensions and tamely ramified extensions, and then we saw two nice applications of Krasner's lemma. One came in characterizing tamely ramified extensions. We used Krasner's lemma, and then having characterized all the extensions, we could apply Krasner's lemma or a consequence of Krasner's lemma, and we concluded that there are only finitely many extensions of a given degree. So if you give me an n, there are only finitely many extensions of degree less than or equal to n for a periodic field, where P is not the Gothic P, usual P, meaning a finite extension of QP. Okay, so we saw these two applications. Today we will start with chapter 3 of Lang. So let's start. So setting is once again global in the sense, I'm not assuming DVR, quotient field of DVR and complete with respect to the valuation. I'm not assuming that. That's what I call local. Global meaning we are studying Dedekind domain and quotient field in general. Okay, the prototypical example is integers when I say global, Z. And the prototypical example of local is a ZP, periodic integers or periodic numbers QP. Okay, so the picture is back to chapter 1 notation. It is Dedekind K is its quotient field, E over K is a finite separable extension, and B is the integral closure of A in E. This is the setup in chapter 1. And we are going to take an additive subgroup of E, right? E is a field, so with respect to plus, it's a group. With respect to multiplication, the non-zero numbers is a group. We are taking E with plus with the given addition. So take an additive subgroup. L is a subgroup of E with respect to plus. And we are going to consider what is called the dual module. The dual of L, which is defined as L prime, is our notation, and it is defined as those x in E such that for all L in L, when you multiply XL, and if you take the trace from E to K, that is contained in A, that belongs to A. Okay, so those x in E such that the trace of XL is contained in the ring of integers downstairs. Okay, so this might remind you of, when we were doing fractional ideals, we had defined A inverse. For an ideal A, for a fractional ideal A, we defined A inverse, right? We showed that non-zero fractional ideals form a group and all that thing. So at that time, we defined A inverse, and what was the definition of A inverse? If you have a fractional ideal A, and let us say quotient field is K, then these were X in K such that XA is contained in A. So this is similar, but I am applying trace. Okay. So it's not that XL is contained in B. I'm not saying XL is contained in B, but I'm saying trace of XL is contained in A. So this is the definition of L prime. I hope the definition is clear. You can check easily that L prime is also an additive group. If X and Y are there, then X plus Y is also there because trace is additive, and X plus YL is XL plus YL, and trace is additive. A is additive. A is closed under addition. So L prime is clearly an additive group. And also note that if AL is contained in L, then so what is the meaning of AL is contained in L? L is anyway contained in AL because A contains 1. So if AL is contained in L, then AL prime is contained in L prime. That's also an easy check. If you take an element A in A and X in L prime, then you want to show that AX is also in L prime. So you have to take AX times any element of capital L, and so AXL can be written as XAL, and AL is contained in L is your assumption. So XAL, the trace will be in A. So AX is also in, so this is easy check, straight from the definition. AL prime is contained in L prime. Also, if L and M are additive subgroups of E, and suppose L is contained in M, then what will be the relationship between L prime and M prime? Can one of you first make a guess, and then of course your guess will be right. I mean, it will be easy to check. What's your guess? Without what would be your first guess?
L prime contains M prime.
Correct. That would be your the way things are set up. That would be your natural guess. It will be containment reversing. It's a dual after all. And once you see that, it can be easily checked. If you take something in M prime, if X belongs to M prime, then XM is trace of XM is contained in A. But if trace of XM is contained in A, then of course the trace of XL is contained in trace of XM that is contained in A. So you are right. M prime is contained in L prime. So it's inclusion reversing, obviously. Okay. Now, suppose you have a basis of E over K, W1, etc., Wn is a basis of E over K, and suppose L is the additive group L is of this form, AW1 plus etc. plus AWN. So such a thing is called a lattice, A lattice. Okay. So L for a lattice, so A lattice, and then we claim that L prime is of similar form, AW1 prime etc. AWN prime. Can you make a guess what are these WI prime? Take a guess. I mean, without thinking, I just want you to have some familiarity with some of these notions.
Like, do we know any elements in L prime? Do we know any elements in L prime?
We are going to claim that L prime is this, if L is of this form.
Yes, but like I'm just asking from the definition, do we know that something obviously lies inside L prime?
Well, not that obvious maybe, but if you check certain things, some things are clear, no? For example, if X is from, if it depends on L, right? It depends on L.
What if you take X belongs to L, then it will, right?
If X
not
clear, no, because even if X belongs to L, then first of all, XL is contained in L or not, you don't know. But even if it is trace of L contained in A or not, you don't know. So since L is defined very generally, there's nothing that we are concluding. But we will take specific L's and then we know things.
Okay, X belongs to A. Can we say that we can?
If X belongs to A, then trace of no, even then you can't say because you know nothing about L, no. That X will come out, but trace of L is contained in A or not, who knows? Right, L is something very general, no. So in general, what can you say? Nothing. But we are going to take specific L. This is our starting thing. Suppose L is of this form, then you can write down L prime explicitly. And my question was asking you to make a guess. What are these WI prime? What will be the natural thing that you are thinking of?
Like normally, like I would guess equal to, but the title says complementary module, so it seems like you're not.
Yeah, that is the name that Lang is giving, but I use the word dual here. L prime is the dual of L or complementary module of L, but and it involves a trace. So trace plays a role certainly. So now can you make a guess what these Wi primes are? They will also be a basis, but what is its relationship with the given basis Wi?
Trace of WI.
Hmm?
Trace of WI.
Trace of Wi will be in K, no? Then it cannot be a
It
basis of E
will
over.
be in A actually.
Yeah, so
Oh,
that cannot, no, it will be in K, it need not be in A because
yeah, it will
Wi
be in
need
K.
not be in B. But so that cannot be a basis. Wi prime are also a basis of your. We have seen all these things long back. There's a very natural basis that you will consider. Given a basis, there's a natural notion of another basis, no? And the word is dual. So what is it?
Oh yeah.
Dual basis, right? With respect to any bilinear form, you have the notion of dual basis. B Wi prime is
Yeah,
delta.
so we take WI prime as that the trace of WI WJ is delta IJ.
Yes, exactly. So Wj prime traces delta ij. So that's called the dual basis with respect to the trace. With respect to any bilinear form, you can have the dual basis. So this is the dual basis with respect to the trace. And this is the claim. And once you make the claim, it's not difficult to prove. So let's prove this. But before that, a word. Sometimes, people call a span of a k basis in E. That's exactly what this is, right? This is a k basis in E and taking the a span. That is called an A lattice in E. The word is usually used when A is a ring of integers in a number field, Z lattice, etc. But sometimes this also can be called a lattice. So the assertion that we are making is if L is a lattice, its dual is also a lattice. Because again, it's a span of a basis. Okay, so dual of a lattice is the plain English way of saying this. And to see this, why this is true, it's easy. So take alpha in L prime, and I want to show that alpha belongs to the right hand side. Okay, so write alpha as a1 w1 prime etc. This you of course you can write. Why? Because where ai belong to k, because wi prime is a basis. So you can do this basis of E over K. So you can do this. And now you take trace of alpha Wi, and by the definition of the dual basis, this will be what? This will be AI. The rest of the things will be zero. So this will be AI. And therefore, what can you say about AI? So you can say that AI belongs to A. Why is that? Why is that? Because alpha is in the dual module. Alpha is in L prime. So by the definition of L prime, what is the definition of L prime?
Which direction are you proving there?
I am proving this containment. I am proving L prime is contained in this thing. Okay. So the definition of L prime is trace of X as a trace of XL is contained in A. So here you are saying that trace of alpha is in L prime. So trace of alpha times anything in L is contained in trace of anything in alpha times L is contained in A. Wi is in L, no, because L is AW1 plus etc. So by definition of L prime, this is contained in A. But that is equal to AI, so AI belongs to A, and this is true for each I. So you have shown that alpha belongs to AW1 prime plus etc. So L prime is contained in this because alpha is in L prime. Clear? So that is just applying the trace, nothing else. So for the converse,
That is just like delta IJ, right? WI prime WJ. So
that's what
the
you
linear combination will be in A.
that's what you used here.
Yeah, no, down I'm saying for the converse.
For the converse, what are you saying? Yeah, if you take something in this, you have to show that it belongs to L prime. Yeah, you are right. That's it. So if you take an element, if you take Wi prime, if you take an element from this, you have to show that it belongs to L prime. So if you take AWI prime times L, and if you take trace, then right, you have to show that this is contained in A.
Yeah, so you take something in L, like summation alpha I.
L, that is summation alpha j wj. So this A will come out because it's trace. Something A will come out. So what you will have is wi prime wj, and that will be non-zero only when j equal to I.
So you just remain left with alpha I. So you will just say A alpha.
Yeah. So it will belong to A. So that is because L is given to be combinations of summation AI WI, where AI belongs to A. So that's all that you're using. The other direction is also true. Okay. So what is the conclusion? The dual of a lattice is again a lattice. And this is useful in various places. For example, you can take a fractional ideal. So we have defined dual, the notion of a dual for any additive group. So if you have a fractional ideal, you recall what is a fractional ideal of B? It is a module, it is a B module contained in the quotient field of B. So it's a B module contained inside E with the property. What is the property? There's a non-zero number, there's a non-zero element in B, let us say C, such that C times this fractional ideal. So fractional ideal is contained in the quotient field E, but C times this B fractional ideal is contained in B. But it's a module. In particular, it's an additive group. So dual of a fractional ideal makes sense because for any additive group, we define the dual. So you can consider the dual of B, and we are going to claim that the dual of B is also a fractional ideal. That's the claim. Okay. So if you start with a fractional ideal, you can take prime, B prime, that is a dual of the fractional ideal, and the claim is that this is also a fractional ideal. So recall the definition: B is a B module contained in E such that there is some non-zero element C such that CB is contained in B. And we have shown long back, the very first lecture on this global thing, so lecture 5, we showed that under the assumptions of A being Noetherian and A being integrally closed, we showed that if you take B, the integral closure of A in a finite separable extension, then B is finitely generated as an A module. In fact, our proof was that B is contained in AW1 plus etc. AWN for some basis WI. We showed this. So B is contained in the A span of a basis of E over K. This we showed long ago. This is the reference if you want to double check. And is it an extra space here? Maybe, maybe not. So B is contained in the A span of this we have shown earlier, and therefore what can you conclude? Therefore it follows that we have a basis Wi such that B is contained in AW1 plus etc. AWN. Why is that? What we know is B is contained in the A span of some basis, but because B is a fractional ideal, CB is contained in B, and B is contained in some A times something plus A times something plus etc. So B is contained in A times C inverse of that plus C inverse of that etc. So you can call that to be the new basis. So B is contained in this, and therefore if you take the dual of this, right? If M is contained in L, then L prime is contained in M prime. So the dual of this is contained in B prime. So B prime contains a lattice, right? Dual of this is another lattice. We just showed that dual of a lattice is a lattice. So B prime contains a lattice, and in particular B prime is non-zero. So this answers your question. In some interesting cases, we know it is non-zero. Okay, so B prime is non-zero. And we are going to show that B prime is also a fractional ideal. So here we use the fact that B is contained inside a lattice, but B also contains a lattice. B contains a finitely generated module of this form. B also contains a lattice. Why is that? That's also not difficult. You take an integral basis Vi of E over K. What is an integral basis? It's a basis of E over K, but all the Vi's are also in the ring of integers, in the integral closure in B. Vi also belong to B, and Vi is a basis. This is of course possible, right? You can take any basis and you can make the basis elements integral. How do you do that? you know that if you have something, you can multiply by, so each of the Vi, if you take Wi to be a basis, each of the Wi you can make integral by clearing the denominator, I mean suitably multiplying by something. If you take the product of all that and if you multiply, you can make everything simultaneously integral, and that will be a basis. So this we have used in the proof of that result. So you take an integral basis, therefore B contains AV1 plus etc. AVN. You agree? Because VI's are now integral. So B contains AV1 plus etc. AVN. So B contains a lattice. And now if you pick any element small b, then yeah, this is a typo. Pick B in the ideal B, in the fractional ideal script B. So this is not capital B, but script B. Then B contains BB, right? B is an element from B. So B contains ideal generated by B. And since B contains this lattice, this ideal will contain this lattice, ABV1 plus ABVN, etc. So this contains a lattice. So the fractional ideal contains a lattice. So by dualizing, B prime is contained in the dual of this lattice, but the dual of a lattice is a lattice. So B prime is contained inside a lattice. In particular, B prime is a finitely generated A module. Right? If B is a module, then B prime is a module. If B is an A module, then B prime is an A module. So that is okay. Finitely generation follows because it is contained in a finitely generated module, and we are over Dedekind ring. So Noetherian is there. So submodule of a finitely generated module is finitely generated. So B prime is contained inside a finitely generated module, and therefore B prime is finitely generated as an A module. Okay. But B prime is not just an A module. We want to say that it is a B module. And that is easy to check from the definition. So this was a definition of B prime. So in order to show that it is actually a B module, you have to take X in E and B in B, and you have to show that Bx belongs to B prime. So if you take beta from B and X in B prime, you have to consider trace of beta X B, and this is trace of X beta B, and beta B is contained in B, because B is a B module. So beta B is contained in B. So this is contained in trace of XB, but X is from B prime. So this is contained in A. So it's actually a B module. And it is finitely generated as an A module. Therefore, it's finitely generated as a B module also. So what you have shown is that B prime is a B module contained in E, of course, by definition. You have to show that it is a fractional ideal. So you have to show that there is an element such that with which if you multiply, then that times B prime is contained in B. So let us take a C such that CB VI prime is in B for all I. Right? BVI prime is a basis. You can make that basis integral by multiplying suitably. So choose such a C for the dual basis. You make the dual basis integral for all I.
VI prime.
VI prime is the whenever I put prime for a basis, that's a dual basis.
So VI prime is the basis of small b, and VI is the basis of small b, and VI prime is the basis of
VI is the basis of E over K.
Oh.
Vi is the basis of E over K, but I have chosen Vi to be integral, meaning Vi's are also integral elements. So Vi belong to B, Vi belongs to B, but it's a basis of E over K. We don't talk of basis of B over A because we don't know whether it is free. We only know finitely generated. We showed free only when A is a PID. Here A is general Dedekind. So we will not talk of basis for B, we will talk of basis for E over K, but the basis elements are chosen from B, which we can do. And whenever I put a prime, it's a dual basis with respect to the trace. So take the dual basis for these VI's and make those integral. VI's are integral, but VI prime need not be, but make those integrals suitably. And then you can check that CB prime is contained in B. So B prime also can be put inside B by suitably multiplying by a non-zero element. Okay, so what we have shown is B prime is a fractional ideal. So dual of a fractional ideal is a fractional ideal. Okay, this will be very useful soon in the next class. So as a small exercise, you show that B is contained in B prime. That's clear, right? If you take B to be your ideal, then B prime is bigger than B. B is contained in B prime. Why is that? If you take X in B, then X belongs to B prime. Because if you take X in B, then X times B is contained in B. And trace of an element of capital B belongs to A. Why is that? If you take an element in capital,
because it's integral over A, right?
yes, because trace of integral is integral. Trace of an integral element is integral. So therefore, if you take an element in B, its trace will be integral over A, and therefore it belongs to A because A is integrally closed. So that shows B is contained in B prime is obvious. We have already done. Also check this. This is also a small check, easy to check, that the dual of a fractional ideal. For fractional ideal, you have another notion of dual, which is its inverse, which we have shown earlier. So what is B inverse? Set of all x in E such that xb is contained in B, capital B. That is B inverse. And you have this fractional ideal. So B is an ideal, its dual is a fractional ideal. So you have this fractional ideal, you have this fractional ideal. You can take the product of these two fractional ideals, and B prime is nothing but that. So the dual of a fractional ideal has another description in terms of the dual of the unit ideal and the inverse of the fractional ideal. So please check that also. It's immediate from the definition. So check this also. So I saw this nice English sentence expressing this relationship as the dual of B prime is a distinguished dual, in the sense it is a fractional ideal that controls the dual of every fractional ideal. If you have any fractional ideal, its dual is controlled by this, in the sense this determines it. You can take the inverse and multiply with this, and that is exactly this dual. So this dual has a nice description in terms of the dual of the most important fractional ideal, which is the unit ideal. Not most important, but the most obvious fractional ideal, which is the unit ideal. So this sentence I saw in this reference. I'm in my class, Arindam. I'll call you later. I'm in my class. I'll call you later. So yeah. So okay, this is something that you should do. It's easy. So to continue, we are going to. So today maybe we'll stop a bit earlier, but we will prove a very nice result that. In one particular case, I want to write down the dual basis. I want to write down the dual module. Okay. So there is a particular case that we have dealt with many times in chapter 1. You know, our usual notation will be A is Dedekind, K is quotient field, E is a finite separable extension, and B is the integral closure. And we would have proved many results. But then we had some explicit results under one more assumption. Right, we had this explicit factorization and all that. Under what assumption? Do you remember that assumption? On B, you put a very important assumption, and then you have many more interesting results. Do you recall? So B is generated over A by one element. If B is A bracket alpha, then you have more results. Okay. So under such a condition, B equal to A alpha, I would like to know what is the dual. What is the dual module? So before that, as you know, the dual module has a close relationship with respect to dual basis. So here is a very nice result about the dual basis. Suppose you have a finite separable extension, then of course by primitive element, there is one element which generates it. So we can call it K alpha. And therefore, since you have this distinguished element alpha, you can look at its minimal polynomial. So let's call it F. F is a minimal polynomial of alpha over K. And I'm going to write fx by x minus alpha, right? Alpha is a root in some algebraic closure. Of course, it belongs to E, but the other roots may not belong to E, because I'm not saying it's normal, only separable. So, but in any case, you can write down fx by x minus alpha. That will be x minus alpha 1, x minus alpha 2, etc. The other roots, you can multiply it out and write it as a polynomial where bi's belong somewhere. Okay, so write like this. Then the claim is, so what is the obvious basis of E over K? The obvious basis of E over K is 1 alpha etc. alpha power n minus 1 because degree is n. So that is the most natural basis, and we want to write down the dual basis in terms of this data f. And the answer is the dual basis is given by b0 by f prime alpha. F prime is a formal derivative. b1 by f prime alpha etc. bn minus 1 by f prime alpha. Okay, so there is an explicit dual basis in terms of the minimal polynomial. So let's prove that the degree of f is n because k alpha over k the degree is n and f is the minimal polynomial. So degree of f is n and therefore it will have n distinct roots. Why n distinct roots? All the roots are distinct, right? Because it's separable. Separable. Okay, so it will have n distinct roots and that we are going to use. So let's call them alpha 1 etc. alpha n. Alpha is a distinct and it is the same n. Okay. Now consider an r which is less than or equal to n minus 1 and consider this polynomial expression. So x power r, for each r consider x power r minus this expression, summation from 1 to n fx divided by x minus alpha I times alpha I power r by f prime alpha I. What is the degree? So this is a polynomial in x. What is the degree of this polynomial? Here it is r which is less than or equal to n minus 1 and fx has degree n and you are taking one x away. So this also is degree n minus 1 or less. So overall the degree of g is less than or equal to n minus 1. On the other hand, if you plug in alpha I, any one of this, take any alpha I and plug in alpha I, what is g of alpha I? What is g of alpha I?
One of the other alphas is
Oh, sorry, think about it. G of alpha I, this will be alpha I power r, and in this summation what will happen? What is f of alpha I?
Just the one term will remain.
Let's say alpha j. Okay, so what is f of alpha j by x minus alpha j? F of alpha j by x minus alpha, f of alpha j by x minus alpha I.
F of alpha j by alpha j minus alpha.
Yes, f of alpha j by alpha j minus alpha I. What can you say about that?
That is 0.
That is 0.
J is equal to I.
Is 0. So that is 0. So all those will go. So only
unless j is equal to I, right? Unless j is equal to I, then we need to
assume j is, so in this summation all terms are coming. So if j not
term will be remain,
j not equal to I, this term is 0. So in this summation only j equal to I will remain. And when j equal to I, what can you say about this? So here you have x minus alpha I cancels and you have all the other terms, x minus alpha 1, x minus alpha 2, all the other things, x minus alpha j with j not equal to I, that is fx. So when you plug in alpha I, what will happen?
I think it will cancel out by f prime of alpha I or something. F prime of alpha j will also look like that, right?
Correct, exactly. So if you look at f prime of x, f prime at alpha I will be exactly what is remaining here. So that cancels with this. So what is remaining is alpha I power r.
So
this is also alpha I power r. Right? So the conclusion is g of alpha is 0 for each alpha I. So what can you say about g? Degree is less than or equal to n minus 1 and it has n distinct roots.
G equals 0.
G is identically 0. Okay, so G is identically 0 and therefore you have got a nice expression. This summation is nothing but x power r. Okay, keep that in mind. So, and the next observation is if you take these polynomials, whatever is coming inside fx by x minus alpha I times alpha I power r by f prime alpha I, all these things are conjugates to each other. That's clear, no? Because if you apply sigma, sigma is a Galois element. Sigma of alpha is some alpha j, and sigma will fix the coefficients of f, and sigma of alpha is alpha j. So these are all conjugates to each other. Now you define the trace of a polynomial as trace on the coefficients, and define like that, the natural definition, you take the trace of this polynomial. So what can you say about the trace of this polynomial? So trace of this polynomial, what can you say? So this alpha is one of the alpha I, right? Alpha is one root and all the other roots are alpha j's. So these are all conjugates to each other. So trace of this is sum of all these things. Yeah, trace of this x minus alpha is exactly this summation. And what is this summation? What did you show? G is identically 0. So this summation is x power r. Okay. So if you take trace, the conclusion is trace of this is x power r. And what is the definition of trace? On the coefficients you apply trace and leave the variable x as it is. That's my definition of trace. So from this you can compare the coefficients and what will you get? So if you compare the coefficients, what is fx by x minus alpha? It is b0 plus b1x plus etc. So what will be the coefficient of x, for example? It will be b1 times alpha power r by f prime alpha, trace of that. But the coefficient of x on the right hand side is 0 unless r equal to 1. So the conclusion is bi, so you get that trace of alpha power I bj by, right, from here you have bj and here you have alpha power I by f prime alpha. What is the conclusion? This trace is precisely delta ij. If you have I here and j here, this will be the coefficient of x power j. This will be the coefficient of x power j, and you are comparing x power j and x power I, so it is delta ij. So
where did r disappear? Can you just repeat that calculation? R should be coming somewhere, right? Can you just repeat that calculation?
No, R is this R.
Yeah, so it should be coming somewhere in this trace, right? I'm thinking that.
So what, once again, what is fx by x minus alpha? It is summation bi x power I, right?
Yes.
So this polynomial is what? This polynomial is summation bi alpha power r by f prime alpha times x power I. But trace of a polynomial is trace of the coefficient times a variable. So trace of this polynomial is summation trace of bi alpha power r by f prime alpha times x power I, bi x power I. Okay. Now that is equal to x power r. So that means the coefficient is 0 unless I equal to r. And when I equal to r, the coefficient is 1. No, coefficient of x power r is 1.
Okay.
So conclusion is trace of alpha power I bj by f prime alpha is delta ij. This j is this I is r here, and j is the coefficients. Just compare, just apply trace and compare the coefficients. Only the coefficient of x power r is 1, all other coefficients are 0. That's exactly this. Okay, so this is what we wanted to prove, right? Our claim was the natural basis alpha power I, its dual basis is given by bj by f prime alpha, and that's exactly what we have shown. So this was the claim. And there's a nice corollary to this claim, which is that suppose you assume B is A bracket alpha. So this is an extra condition. This is not always true. As a ring, it is generated by 1 alpha. We know that B is finitely generated as an A module. And now we are claiming that it is as an algebra, it is generated by 1 element. Suppose this is given to you. And then the dual module of B has a nice expression in terms of the minimal polynomial. It is B multiplied by 1 by f prime alpha. This follows from the previous result because what you do is fx. Suppose fx is given to be this polynomial, the minimal polynomial of alpha. Write it as x minus alpha times something. Okay. From this, what can you conclude? You know that bn minus 1 is 1. Compare the coefficients. Bn minus 1 is 1. And you know that bn minus 2 minus alpha bn minus 1 is an minus 1. So bn minus 2 you can express in terms of using alpha and an minus 1, etc. So you will get some number of relationships between AIs and BIs and alpha, and from that you can conclude that the A module generated by alpha power I is same as the A module generated by these BIs. By comparing these coefficients, you will get some relations. Using those relations, you conclude that the A module generated by alpha power I, which is precisely this, is same as the A module generated by BI. In other words, B is nothing but A plus A alpha power n minus 1. That is what is given to you, is same as the A module generated by BIs. Okay, but what is B prime? B prime we just proved that we know that a lattice, its dual is also a lattice, and it is given by the dual basis. And we know that the dual basis of alpha power I is bj by f prime alpha. So the dual basis is these things. So b prime equal to a times this plus a times this, because this is the dual basis and it's a corollary to that. But we just saw that the module generated by alpha power I and the module generated by bi are the same. So AB naught plus etc. AB n minus 1 is same as A plus A alpha plus etc. which is B. So this is nothing but 1 by F prime alpha times B, and that is the corollary. Okay. So the dual module, we have introduced this concept of dual of any additive group, and dual of B has a nice expression when B has a particular form. When B is of that form, then the dual of B has a nice expression. Okay, all this we are going to use later. Now you remember when A is a DVR, when A is a DVR, and suppose there's only one prime P above P, this is an extra assumption, there's only one prime, and assume that B by P is separable over A by P, our standard assumption, and then we are going to claim that there is an alpha such that B is generated by one element. There's an alpha which generates B over A as an algebra, as a ring. Okay, so this is the following is true. The integral closure of A in a separable extension of the quotient field of A is indeed generated by one element is true if A is a DVR with the assumption that there's only one prime lying above P. Right? A is a DVR, so there's only one prime below, and assume there's only one prime above, and then we are going to show this. So what is the proof? So in particular, this applies to the chapter 2 of Lang. This applies. Why? Because in the p-adic context, we know that it is a DVR. Right? By definition, we looked at DVR. Extra thing was complete with respect to the valuation. It's a DVR. And there's only one prime lying above, we have proved. So it's exactly that context. Therefore, in that notation, we know that there is an alpha in OE, the ring of integers of this extension, such that OE is given by O bracket alpha. So this is true in the local situation because of this result that we are going to observe. So first of all, let me recall another result that we did. So this is page 11 of lecture 12. When A is a DVR with quotient field K, L over K finite separable, B integral closure of A in L, and only prime lying above, because it's a DVR, it is generated by one element, we call it pi, and beta be any element such that the reduction mode P generates, right? It's separable. So there's a primitive element, let it be of the form beta plus P, where beta belongs to P. Then we prove that B equal to A bracket beta comma pi. Do you recall this proof? What was a crucial ingredient in this proof? There's only one word in this proof. Do you remember? Does anyone remember? At that time also I said, I titled it by that word. Okay, there are many ingredients, but at that time there was one crucial ingredient. Nakayama, yes. Nakayama, and the other ingredient is we had already shown the summation EIFI equal to degree of extension. So one thing from that proof also we used. Okay, so when it's DVR, you know that, yeah, we counted the dimension of a vector space, right? D by P over A by P, we counted that dimension, and that idea was also used, and then Nakayama. So here is a full proof. I have put the full slide. So we took C to be this right hand side ring, and we want to show that C is equal to B. So in other words, B by C is 0, and B by C is 0 is same as showing PB plus C is B. Then B by C will be 0, and PB, there's only one prime lying above, so it is of this form. And from our earlier computation, we know that these things will generate B by P power E over A by P. Because B by P over A by P is generated by beta plus P, and P is generated by this pi. So put together, these will generate. And so if X is in B, then if X is in B, then X minus, this is over A by P. So X minus a multiple of P belongs to C. So this is what we wanted to show. If X belongs to D, then this is what we are showing. And this proves this. And by Nakayama, it is done. Okay, so by Nakayama, so we have shown that D by C, what we have shown is, so this divided by C, right? D by C is this divided by C. This divided by C is P times B by C. So P times B by C equal to B by C. And B by C is a finitely generated module because B is a finitely generated module. So you have got a finitely generated module, and DVR, so it's a local ring. So in order to show for the maximal ideal, so P times B by C is B by C, and B by C is a finitely generated module. So by Nakayama, B by C is 0, and that was the claim. Okay, so this is what we did. We can push this a little bit further, and let's do that. So let P be the minimal polynomial of this beta plus P over A by P, and choose any monic polynomial in A whose reduction mode P is this minimal polynomial capital P. And then, so this is just basic computation, formal computation. You check that, you take beta plus pi and you check f of beta plus pi. You will see that modulo p square, it is f of pi plus f prime beta times pi. So this you just have to check, take a polynomial x square plus ax plus b and substitute this, expand this and verify this. You will get this. So that's an easy check which I leave. You will get this, and you will get it in such a way that f prime b is non-zero. F prime b is non-zero mod p. You will get this much. So because f prime b is not 0 mod p, what is the valuation of this? Valuation with respect to capital P. What is the valuation of this? Remember, pi is a generator of this ideal. So pi has valuation 1. So what is the valuation of this? This has valuation 1. So what is the valuation of this product? Valuation is additive. A valuation on product is sum of the valuations. So this means f prime pi is not in P. So that's a unit. So what is the valuation of this? This has valuation 1. Right? Because of this condition, this has valuation 1. So
Yes.
yeah. Therefore, and you know that this difference has valuation at least 2. This difference, this minus this whole thing is in P square. Valuation at least 2. So what can you say about the valuation of f of pi, f of beta? There are two possibilities. Either f of beta has valuation 1 or f of beta has valuation can f of beta be a unit? Can f of beta have valuation 0? No, right? Because if you reduce mod p, you have the minimal polynomial and p of beta plus p is 0. So right? So f of beta certainly has positive valuation because f is chosen such that f bar is a minimal polynomial. So this has positive valuation. Now the possibilities of valuation is equal to 1 or valuation is strictly bigger than 1. Suppose valuation is 1, then we are done. I mean, we will choose f of beta. If valuation is bigger than 1, what can you say? If valuation of this is strictly bigger than 1, then what can you say about the valuation of this? Valuation of
It will be 1, right?
Yeah, it will be 1 because valuation of x plus y is bigger than or equal to minimum of valuation of a valuation b with equality if these are different. So if this is strictly bigger than 1, this will have valuation 1. If this has valuation 1, what will be the valuation of this? It will be 1 because this difference has valuation at least 2. So again, it will be the minimum. So if so, the conclusion is either this has valuation 1 or this has valuation 1. One of these two certainly has valuation 1. Okay. So therefore, either this or this, one of these two has valuation 1. With respect to capital P, valuation 1. You can also check that this will also generate this extension. B by P over A by P is generated by this, but it will be generated by this or this also. This also you can check from the definition of F bar is P. So in other words, so call this element alpha. Alpha plus P also generates B by P over A by P. So what you have concluded from this analysis is you have got an alpha. Alpha is either this or this depending on which one has valuation 1. So alpha has valuation 1. So alpha is also a generator of capital P. Moreover, alpha plus P generates B by P over A by P. So if you go back to what we have already concluded using Nakayama, here you have, a generator of this ideal and a generator of this field extension, beta. Put those two together and you have got the full thing. What have you concluded in the next slide? You have got an alpha which generates this ideal and which also generates this extension. So in this proposition, you can choose this and this to be the same alpha. You have manufactured such an alpha. So if you apply to this proposition this choice of alpha, you have got, so in the Nakayama argument of the previous slide, we can take both those elements beta and pi both to be alpha, concluding that B equal to A bracket alpha. So this is the proof. So in DVR with only one prime lying above, you have this nice condition, and this is a nice condition under which we have explicit factorization of prime, and we also have the dual module is 1 by f prime alpha b, etc. Right, this kind of nice statements. Okay, so maybe we are stopping a bit early today. I will finish the lecture part here, and if you have questions we can discuss, and then we will stop. So we'll continue with this thing. So the point is, using this, we will define a very famous ideal of B called the different ideal. Different, D-I-F-F-E-R, usual different. Okay, that will be the name of the ideal, and we will also have what is called the discriminant ideal. So there will be what is called the different ideal above in B, and they will be the discriminant ideal in A. These two ideals will be related by the norm map. Norm of ideals we have introduced, and these two will be related by the norm map, and these ideals are very important in studying ramification of primes. So long back Manav had asked, why are we not doing many examples? I said you should do examples, but I am not spending so much time because many of these examples will be much easier to do with more theory. So first of all, we have stated an explicit factorization result. I said you should read the proof. I am skipping the proof. And now with this notions of different and discriminant, they are intimately connected to ramification. So how primes ramify is much easier to study after these notions. And we are introducing this notion of dual module, dual of an additive group, in order to introduce this concept of the different ideal. and then we will have the discriminant ideal, and that is these are the main characters of chapter 3. Okay, so let's stop here. Let me stop sharing the screen, and let me stop the recording also. Okay, so if you have questions, please ask.